Hello, my dear friend. Hello, my dear friends. This is Dr. Mohamed Nezami. I welcome you to my video channels. I know this is the second season of my radio frequency and microwave device and circuits designs. I started this a year ago. I have already in my video channels on video channel on the YouTube. I have about 40 videos so far on various ways of designing devices and transceivers and antennas, amplifiers, and so forth. And I decided to start another season. And this is the first of 3 videos that are going to be on non-reciprocal devices, primarily the circulators and isolators, okay? Now, this is my phone number. I have spent a lot of years working in the US, and now I'm based in Jordan, Jerash, Jordan. So if you need to get in touch with me for any consulting, I do RF and microwave circuits designs. I do my own. You give me the specifications and you give me the concept, and I realize it for you in hardware, anywhere from DC to 35 gigahertz. I do my own system modeling. I do my own circuit layout. And what you get is basically the fabrication files, Gerber files, and or ODB++, and you get, I present the design along the way to you and your engineers so that I'm actually almost like working with you. And I have some very happy clients that I've worked with in Europe, in the United States, in India. So if you have if you need to outsource some RF board, please do reach me at this number, or you could contact me at this email, okay? I can also be contacted using the Android's apps like WhatsApp and Telegram on that same phone number that you have right here. Okay, so today the reason I decided to do this 3 videos on circulators and isolators is because really it's a device that is interesting, and its modeling, the design and modeling, it involves very interesting aspects of both electromagnetism and electromagnetic waves, electrical waves. So it's a device, basically. I'm not gonna be down to the 0 level of designing these. I'm assuming that all of my videos, I assume that you have familiarity with the concept. So this is advanced design methodologies. I design the system, I present the theory, then I use modeling. In this case, in this particular case, I'm not using the any of the path wave type Agilent or Keysight tools. I'm using, in this case, 3D modeling, HFSS from ANSYS. You could also utilize CST and all of the other packages as well. So it's an interesting device because it combines both electrical and electromagnetic techniques. So let's roll in. First of all, before I do that, I would like to remind you that please sign up for my channel. Click the sign up so that I increase my presence in the on the web, and please share it if you could. I would appreciate it. Okay. So what are circulators and isolators? First of all, when we say circulators or isolators, really it's just one device. It's an isolator, okay, that has a 3-port. It's a 3-port. It's non-reciprocal device, meaning the forward path and the reverse path are not the same, like passive devices like filters and so on, okay? And that's really the key to this device. So we only have circulator. It's a 3-port device that allows electromagnetic waves to travel in one direction and then never go back the same direction. It goes, when it comes back, if there's any reflections, it goes back the other way, to the third port. Now, if you happen to terminate one of these ports, it becomes an isolator, which is basically all it is a two-port device that has either internally or externally a match, a 50 ohm load to one of the ports. So let's just start with, I'm going to start first of all introducing the concept, okay? And we're going to go into both. Basically, this video is really concerned with surface mount planar circulators. So meaning stripline isolator or microstrip line. And these are drop-in devices, meaning that they are devices that are meant to be installed as a drop into a board on the top surface. So I'm going to present the theory for both the strip line and the microstrip line, and then use modeling techniques to present that. So I'm going to present the concept, overview some of the theoretical background, okay, equations on how to design this thing, and then do an example of designing a 6 to 9 gigahertz, so C-band, X-band type device. And so there are going to be 3 videos. On this video, I'm going to introduce the theory behind it, the design principles. And then on the next 2 videos, I will do the HFSS. So the HFSS is already ready. So I have these. This is one of the devices. This is the Microstrip circulator. It has a 3-port device. Okay, so if you look at the excitations, there is 1 here, there's 2 here, there's 3 here. And then it has basically all these parts that we're going to cover. So basically it has a bottom ground piece to the BC board. The green one here is a substrate. In this case, I'm using a substrate that is Rogers 4003 as an example. And then it has a magnet. This is a permanent magnet, the one up here. So let's look at that. That's this piece here, which is a non-model magnet right now. And then what I have is basically this is the copper pieces. Well, let me just show the strip, the junction. This is a junction, a microstrip junction, okay, that is laid out on Rogers. And then what happens is right in the circle, in the disk here, the circular disk, it's in this case, it would act as a cavity, okay? There's the ferromagnetic material, which sits right underneath between the ground plane and between the top layer foil, okay? And so the magnet comes in and it biases the ferromaterial, which is this piece here. And what happens is that the electromagnetic wave will travel only a single direction, like we show here, for instance. Okay, and just to animate this. So right now you can see that the waves are going in here and going out here, and nothing comes to this port here, okay? So, and that's what a circulator is. It means it goes in here and goes, nothing goes that way. And in this example in here, basically I designed it for the band that is shown in here, which is, let's see if you put a marker on the mid band here, and that is, let's see, marker 8.8 gigahertz, okay? We're gonna cover this in much more details on the next video, okay? And in the video after that, we're gonna cover the strip line. And the strip line, basically, it's the same as the microstrip, except half of it is gone, because we're trying to in the first one in here, you've got let me get rid of the electromagnetic field picture in here so you can look at the copper clearly. So you have a substrate, okay? You have a ground in here. That's the ground here, and you have a substrate, and on top of the substrate is this printed line. So this is a microstrip because it doesn't have an upper ground plane as well. So where the strip line, and I'm hoping that you're familiar with strip line and microstrip line because I'm not going to cover that. The strip line is the other way around. It has two ground planes. Okay, so it has one here. Oops. It has one. Look at the copper in here. So it has a bottom ground and it has a top ground. Okay, and in between it has a junction, a microstrip junction with a disk. Okay, as I show here. Just move this out of the way. Okay, as you can see here, there's the Y junction. Okay, and then contrary to the microstrip isolator, it has two permanent magnets, one on top and one on the bottom. Okay, and it's encapsulated. The copper is encapsulated between these two. The whole thing is encapsulated. When you go to, what I do here is I model this thing from an electrical point of view, but eventually this has to go to a mechanical engineer that would actually design it for real life with exact dimension as they are in here to do the CNCing and the other parts. So you have seen, and this one, of course, I did it for, let's see, the frequency response of this one. This is done for 8.9. So I try to do it between 8 and 9 gigahertz. And one of the things that I will show in the videos, in the coming videos, this will be the third video that we got. Well, this is the second one, but the microstrip is going to, well, no, the other way around. Let's do the second is the microstrip. So one of the things that I will show is how can you sweep these parameters to do the optimization, because these circulators in particular, as we will show the theory, it's based on equations that will get you some initial starting point with the design, but once you go into the 3D modeling, then you end up, of course, it won't work like you would want it. You still want to tweak the dimensions so that and optimize them. So what I do in these designs is I parameterize all of this design. So this is a table that shows you all these parameters. They're giving symbols and they're giving values. So what I do is I use either tuning or some optimization. I do sensitivity studies of some certain portions where that for manufacturing, you want to see that you can't do, for instance, this much tolerance. You would want to see before you go ahead and fabricate it or machine it, how critical are some of these parameters. So let's get back to the theory. Let's build some background theory this video, and then on the next video we'll go back to these HFSS models and talk about them. Now, one thing you want to realize is that for the HFSS model, I'm not here to tutor you or on how to do modeling, how to build the model, because I'm assuming that you know how to do the plotting of all these, how to actually build up this model in the CAD system. And that's what I do. I did this, and it takes many hours to get this to work. So I can't really make a video on tutoring on how to, use a circle disk, a hexagon in here, or something, a block in there, a strip line in here, the ferro disk in here, or how to show you, for instance, on how to do the ground plane underneath, for instance, or how to do the vacuum that eventually that you have to solve. All of this, you can go and learn yourself how to do HFSS. I'm assuming that you know how to use HFSS and how to build things into it. So this is strictly a design lecture. It's not trying to teach you how to do the things in the software itself. Let's get back to the circulator. So a circulator is basically a 3-port device, okay, where if you excite the signal on one port, it gets, depending on the direction of the electromagnetic field, whether it's clockwise or counterclockwise, it depends on that, and that way it will decide where the signal will go regarding the other 2 ports. Like for instance, in this case, if you excite port 1 and you have a magnet in here that bias the ferrite in here with a clockwise electromagnetic field, okay? You remember this from high school where they taught you how to grab the wire, and if the current is going this way, then the electromagnetic field is that way, or if the electromagnetic field is that way, the current is this way, or the other way around. Many of you probably remember that. So the signal will go in here and will go only to port 2, and very little will come back to port 3, and nothing will come back to port 3 either way, this way or this way, okay? And on the reverse path now, if a signal comes into this way, and you happen to be counterclockwise magnetic field, all of the signal will go into this port number 3, and very little will get back to 1. And that parameter, in fact, we call it when you excite a signal in the reverse path, and you can measure how much the ratio between this signal and the signal that gets to port number 1 is actually called isolation, okay? So we've got one parameter, which is transmission insertion loss, is between 1 and 2. From 2 to 3 to 1, this way, it's isolation, okay? And then on the same part is return loss. Of course, you still got the return loss on all 3 ports. And in this case, they drew a 50 ohm termination, okay? If you do a circulator like this, then that means you're only interested to pass signal through this way and nothing get back. If something gets back, you would want to route it to a 50 ohm load that will absorb it, and it will not reflect to go back in either way. And that would be the case where one of the uses is for a circulator is we'll go into that in a moment, is for transmitters, for power amplifiers, you know, where if there's any reflections, these reflections would come back to the device and will accumulate in power, and it will burn out the amplifier or the circuitry. So that's one of the ways where you would terminate the 3rd port. But I will show you in a minute, there are some applications where we want this signal, actually. We have a transmitter that transmits this way, and a receive path, where the signal comes back here, it doesn't go that way. It goes this way, and this would be connected to a receiver. And this would be the case of radar system, where you're pulsing a signal, and then you're observing the return back, which will be available at this port. In one-way communication, or where this would be sitting on a transmitter, then that would be only one path. Now, the circulator types, now again, an isolator is basically exactly the same as a circulator, except you're omitting one port by terminating, okay? There are 4 types of circulators. Well, there are many circulators, but the most common ones that are right now that we're dealing with when we're doing transceivers, radio frequency systems for either communications, or radar, or instrumentation, or medical devices, they could come in as connectorized modules, where you would get it with basically either SMA or N or BNC, whatever appropriate to that frequency, okay? Or it could come in as a waveguide, the waveguide, and you can see the magnet is right here. That's where the magnet is, okay? This one has a magnet. It's built into this, right underneath this cover. Or it could be stripline or a microstrip line. A strip line is this one here. This one is encapsulated. In a moment, I will tear down one. I'll show you the tear down of one and show you what the pieces are, just like I showed already in the system on the device modeling using the HFSS that I just showed you. But a strip line is basically where you have this, where it comes in a metal housing. The magnets, the top and bottom magnets are embedded in here, okay? And then the three brass slabs usually stick out. These are the strip lines, okay? So this would come in, and then of course you got 4 mounting screws in here. So this would, the board, in your BC board, you would make a square that is exactly the same size with 4 holes around the sides, and this would drop in, and this will meet the 50 ohm lines. And this one, if it's an isolator, this is the third port. It'll be it'll be connecting to a resistor. Or a microstrip, and a microstrip you can see here. So you've got a substrate, okay, you've got a ground plane, you've got a substrate, in this case, this black piece here. And then you've got a stack of 3 things in this case. You've got the ferrite material, which is here, and you've got a spacer, which is basically foam, just a piece of foam, isolating the mechanically, just misplacing the magnet. This is the permanent magnet on the ferrite on top of it. And this here can come in. You don't have to make a cutout on the board for it like you would for a strip line. This one actually mounts right on top of the board. And then this here, usually this printed line is printed along the side so that you actually can solder to the 50 ohm lines. In this particular case in here, of course, there are some open stubs in here that you see. These are double open stubs. They are basically to do matching between the cavity, okay, the disc, and the 50 ohm line, okay? So what are the applications of isolators, circulators, now that you know what these devices are? First thing is the protection of transmitters and power amplifiers. You know that these devices, given the appropriate power level that they can handle, you can put them on the output of power amplifiers or transmitters. And so that if, for instance, if somebody by mistake turns the amplifier on while there is no load on the output, you get full reflection back. If you don't have an isolator, all of that full reflection will go back to the board and will blow up the board. So a circulator, terminated circulator, in this case, at the output, would absorb that reflection back, and it will not, very little go back to the power amplifier or the transmitter. And in the case of transmitters, of course, say if the antenna is knocked down, now you have an open load. So with an open load, all the waves that reflects back, full reflection back, will be absorbed and will not propagate backward to the electronic circuitry and burn it. Another usage of it, anytime you have a cascade of sub-circuits, high frequency, and you would want to maintain good retain loss between these inner stages because of, you can't redesign the thing, or it has a very dynamic input retain VSWR. So one of the ways to get around this is by doing an isolation between these interstages, is by using an isolator or a terminated circulator, and that way you can actually maintain a good 50 ohm, good resistive 50 ohm, or meaning good return loss. So you've isolated these devices, because if you had a device designed separately and another device designed separately, and once you interconnect them, they interact and they're not anymore meshed. So you get a very bad ripple or reflections and so forth. So one of the ways to go around this is you can put an isolator and it will completely isolate the loading from the interaction of the output impedance and the input impedance of the following system, if you can afford it, of course. The other thing we can use it for is really either power combiners or power or diplexers. And one of the examples that I just showed a minute ago, you can use a circulator in radars. A radar at the output of the transmitter, you've got a circulator that basically feeds the antenna, and then when you signal transmit, it goes one way, and then the return comes back and it goes the other way, and they're totally separate paths. Okay, and same way you could do with the, say, they use them in multi-channel transmitters where you've got a bunch of transmitters that you would want to combine onto one antenna. You could use circulators or circulators for that case. So power combining will cover that. Measurement and monitoring. Of course, you've all used network analyzer and PNA and VNA. All of them, the way they can measure the input return loss and the reflections is actually by using either a circulator or a coupler. The circulator is one of the ways to do it too. So you can isolate the reflected and the transmitted. Okay, so this is a schematic diagram that shows some of these applications. For instance, this is a diagram that shows a typical transmit receive module or TRL module. You've got a switch between the transmit and receive path. So, and then you've got some kind of phase shifter in here. That's for phase arrays, phased antenna arrays in this case. So on the transmitter, you can transmit and then use a circulator between the antenna and the power amplifier. First of all, to protect the power amplifier and to isolate the receive path. So when you transmit this way, nothing will come back this way, very little. Or if there is some that leak into here, it goes in here, and again, it gets absorbed in here. So this is a circulator with one terminated port, meaning it's an isolator, okay, for the LNA, the low noise amplifier. And then on a receive path, signal comes in here, it can't propagate that way. It goes this way onto this, and it goes this way and into this. So the combination of the isolator and the circulator in here is a perfect transmit receive duplexing system. Then in this case, for instance, in here, this is for power amplifiers. Anytime you have power amplifier stages where you would want to do protection and maintaining good return loss, in one particular case is because you wouldn't want any of these devices to oscillate. If you didn't design them carefully and there's a likelihood that these devices will oscillate, the best thing to do is just throw isolators in there. Isolators will make it see always constant impedance, resistive impedance. And this is another one where you can actually do the transmit power amplifier isolation. And in this case, for instance, in this example that I grabbed, somebody was illustrating how you can use two of these isolators if you want to do more isolations, okay? So you get more insertion loss, but you get more isolation because the signal leaks in here, okay, it comes back, reflects back, it gets absorbed in here. If a certain portion come back and you wouldn't want to attenuate that even more, is use another isolator. So it goes in here and then goes in here and very little leaks back, okay? Now, I grabbed from the internet just a few of these example boards, because my presentation, I'm going to present to you the design of both the planar Stripline and Microstrip line circulators, or in this case, also meaning isolator. So this is a board. This is a PA board. You can see a hybrid amplifier with two power amplifiers and the power amplifier devices in here. And you can see the combining in here and the input formation in here. Okay. And at the output, you can see that there is an edge coupled directional coupler in here to monitor for power monitoring. But then also right here is a circulator, which is terminated into a 50 ohm load that is here. What you see here is a 50 ohm resistor that is high power 50 ohm resistor in this case. This is probably look like maybe I would say about a 10 watt to 50 watt resistor. The amplifier, of course, you can see that you can trace back the amplifier from here. You have a splitter that splits the signal in two paths. You have two amplifiers in here just to build up the power level, drive level, and then you combine it again and go into another driver, okay, and then you go into this device here, which I don't know what this is. It might be a circulator, might be a low power circulator, although no, this is probably a filter, a harmonic filter. And then you go in here, and of course, this is your PA, and the output of the PA goes into this. This is a stripline circulator, obviously, because it's completely encapsulated in metal, because you always need the metal all around it to come on the top and bottom ground planes. You would want completely seal on it. And of course, the magnets are embedded inside of it. Here's another example of a power amplifier also. The input comes in here. There's a PA device in here, and then you go in here, and there's another power amplifier device in here, and then there is some sort of a directional coupler. You could see that it's a directional coupler. There's 50 ohm terminator in one end, and this is for power monitoring. Or power monitoring to do automatic level controlling or something. But at the output in here, again, what you see is a stripline circulator with a third port terminated into this high power resistor that you see here. Of course, you can see how they made the cutout, the square cutout for the drop-in circulator. You drop it in, you have 4 screws, and you put them in, and then you solder basically the 3 ports to the corresponding whatever comes after. Another example in here that shows another nice board. This is a TR module probably, because you've got a receive path in here. Oh, I know why I included this is because unlike these ones where you're only transmitting and the reflection is actually being fed into an absorptive resistor. So this is an isolator in this case. This one here, you don't see any resistors on the reflection port. This is a circulator in here, and you've got a transmit path on one side, and then another path comes in here, and you do the processing, which means this is a transmit receive application basically. And I think the first one we started was a transmit receive, wasn't it? No, I guess it wasn't. It was the only one here. Okay. So how about microstrip circulators? Well, here's an example. Here's a little TR module. Okay, it looks like a space application module. This is, you can see the cutout in the BC board, and they dropped in this surface mount microstrip circulator. Okay, and in this case, of course, you've got a transmit and receive paths. You can see them right here. You can see that the receive path is here, splits into this 2, or it could be a combiner in here, because you got 2 die packages in here, and the signals combine and going this way, and then going out that way, and the receive path is going this way. Yeah, this is more like a low noise amplifier in here that goes out. So this is full transceiver application. But you can see this here where the magnet is sitting right on top and everything. Okay, so let's now introduce the theory of stripline isolator, or maybe I'll tell you what, let me stop at this point and split this video actually into 2 videos, okay? That's the best way. So, ladies and gentlemen, I appreciate you watching this. Let me make the videos shorter than, I don't want to make them very long so people don't get bored. Again, this is Dr. Mohamed Nezami presenting the design and modeling of both microstrip circulators and stripline circulators as well. Okay, so in the next video, I'm gonna present to you the theory of this, and then we're gonna go from there. Although let me just cover one thing. So how do you design a circulator? Well, start out designing circuit, what's involved? Let me go to ChatGPT, and basically I gave it the question of this. Show me, no, not this, sorry. This one. Design stripline circulator, ChatGPT, okay, 3.5. Well, it says, okay, here it is, it says design stripline circulators involves creating 3-port devices that allows signals to circulate in only one direction. Here's simplified step-by-step guide. That's exactly, I said, why make a presentation slide on this when ChatGPT can put it out for me? So I'm going to just read these, and you can pause the screen and go through them. But first of all, of course, you're given a frequency. You don't choose it, but you're giving an application frequency that you wouldn't want to go and design this at. Then select the substrate. Okay, in the case of Microstrip circulator, in the case of stripline circulator, it's most likely that the substrate, there is no substrate, because the Y junction is suspended and sandwiched between two ferrites and hang in air. So the substrate is really a vacuum. It's air. And then define the dimensions. Well, define the dimensions. That means we have to use the math. And the math, I will show you that from the 1960s, these were derived, these equations were derived and proven. But back then, of course, it used to be Fortran computers, and there's no 3D EMing and all that good stuff that we have right now, that the luxury of HFSS and CST and whatever. So, but still though, we will start with the equations, plug numbers, get values that are going to be messy, it will not work. We go in, build the structure in 3D EM, and then somehow just back and forth until you get it to work with the various ways of doing, either iterating by common senses or doing parameterizing and optimization or sweeping. I use sweeping, I will show you, because there isn't that many things to really design. I mean, you're talking, depending on the frequency and the materials that you have and the magnet and the ferrite, you're going to have basically the radius of the ferrite. Let me get back to this diagram, or let me get back to the more clearer diagram of the Microstrip. So basically, you've got the Y junction cavity, and you've got the diameter of the disk. You've got the line that feeds the strip line or Microstrip line. So you got the width, the thickness of the brass or the printed line, and then you got the diameter of the height of the ferrite, the height of the substrate. So there is not a whole lot of parameters to design, but we have the equations. You throw them in there, you extract some dimensions, you build it in the model, and then you see what you get, and then you iterate from there before you do machining. Okay, so we calculate the coupling gaps. I don't know what that is, but let's add ferrite material, okay, and then design matching network. Of course, that's true. Simulate and optimize, okay, and then fabricate. And then after you fabricate, you test. And then, of course, you will not be happy for some way or another, and you figure out, well, I have to change this parameter that way, and that's where you iterate if necessary. So, and in this case, it says, remember, this is a high-level overview, and the actual design process involves detailed electromagnetic analysis and engineering considerations. It's also worth consulting with an expert. So that's me. For $25 an hour, rate I'm going right now is you can come into me like I did this. This is why this video came about, is because somebody came into me and says, can you please help us design this? Because they had some kind of issue with lead time from manufacturers, and they said, well, this is not that complicated, so let's go ahead and integrate it into the board and build it actually with the because the ferrite, you can get those done. You don't have to make them. You can get them in discs to certain dimensions, and the magnet, you can buy them. So all it is just you figure out the dimensions that you would need to add to the BC board that you have to implement one of these. Okay, so saying here, the actual design process involves detailed electromagnetic analysis and engineering consideration. It's also worth consulting with experts or using specialized software for electromagnetic simulations to refine and validate the design. And that's exactly what I'm going to do next, okay? Ladies and gentlemen, this is Dr. Mohamed Nezami. Thank you again. I will see you in the next video. Now, there are going to be 4 videos on this. So thank you very much, and we'll see you later. Bye.